Hi, I'm Educator in Uplatz. Today we are going to discuss about introduction to multi-core programming. Plan multi-core architecture, multi-core processor, a CPU cache could be a CPU coherence, concurrency platforms, PT threads, TBB, OpenMP, CILK++, base conditions, and CLK screen, MMM in CILK. Multi-core architecture, architecture, multi-core processor, multi-core CPU cache, CPU coherence, power density, watt per centimeter squared versus year, 4,004, 86 in 70s and 80s, 286, 386 in 80s, 486 they outplayed, Pentium processor, then in after 2000 it was used in nuclear reactor rocket nozzles and sun surface in 2010. Intel dual core to duo processor is shown in figure. Dual core CPU core chip consists of CPU core alone cache and through bus interface connected to the cache. Chip multiprocessor consists of various processing elements, a network, a memory, and I/O. Multicore processor. A multicore processor is an integrated circuit to which two or more individual processors called cores in this sense have been attached. In a mini-core processor, the number of cores is large enough that traditional multiprocessor techniques are no longer efficient. Core on a multi-core device can be coupled tightly or loosely, may share or may not share a cache, implement inter-core communication methods are besides possible. Cores on a multi-core implement the same architecture features as a single core system, such as instruction pipe parallelism, vector processing, SAMB, or multi-threading. Many applications do not realize it. Large speed factors, parallelizing algorithms, and software is a major ongoing research areas. CPU cache 1 of 7, main memory, index data, index TG data, cache memory. A CPU cache is an auxiliary memory which is smaller, faster memory than the main memory and it stores copies of the main memory in locations that are expected frequently used. Most modern desktop and server CPU servers have at least 3 independent caches: the data cache, instruction cache, and the translation requested buffer. Each location in each memory main cache has a datum cache line, which ranges from 8, 10, 512 bytes in size, while a datum requested by CPU instruction ranges from 1 to 16. A unique index called address in the case of the main memory. In cache, each location has a tag storing the address of the corresponding cached datum. When the CPU needs to read or write a location, it checks the cache. If it finds it there, we have a cache hit. If not, we have a cache miss. And in most cases, the processor needs to create a new entry in the cache. Making room for the new entry requires a replaceable policy. The least recently used discourse, the least recently used item first. This requires to use the age bit. Read latency. A time to read a datum from the main memory requires to keep the CPU bus busy with something else. Out of order execution, attempt to execute independent instructions arising after the instruction that is writing due to the cache miss. Hyperthreading allows an alternative thread to use the CPU. Modifying data in the cache requires a write policy for updating the main memory. Write to cache, writes are immediately mirrored to main memory. Write back cache, the main memory is mirrored when data is evicted from the cache. The cache copy may become out of date or stale if other process modify the original entry in the main memory. Each location in the main memory can be cached by just one cache location. Each location may be cached by one or up to cache locations. The replacement policy, this is where the cache a copy of a particular main entry of main memory will go. Full associative with any entry in the cache can hold it directly by one push possible entry in the cache can hold it. NB set associative, n possible entries can hold it. The figure directed map cache fill and two-way associated cache fill are shown. Cache performance for spec CPU 2000 by Jan Canteen and MD in cache size and miss rate are given. The spec CPU 2000 suite is a collection of 26 compute internal and non-trivial programs used to evaluate the performance of a computer CPU, memory, system, and components. HTTP www.spec.org OSG CPU 2000. Here, direct, two-way, four-way, eight-way, and full are considered. Cache coordinates. Here, processor P1 reads X is equal to first from the backing store, high-level memory. Next, processor P2 loads X3 from the same memory. The processor P4 loads X3 is equal to 3 from the same memory to another processor. Processor P2 issues a write for X is equal to 5. Processor P2 writes X is equal to 5 in local cache. Processor P1 issues a read X, which is now invalid in its cache. MSA protocol. In this cache coherence protocol, each block contains inside a cache can have one of the three possible states. M. The cache name has been modified and the corresponding data is inconsistent with the backing store. The cache has the responsibility to write the block to the backing store when it is evicted. Yes, this block is unmodified and is shared, that is existing at least one cache. The cache can evict the data without writing it to the backing store. This is block is invalid and must be fetched from memory or another cache if the block is to be stored in this cache. These coherency states are maintained through communication between caches and the backing store. The caches have different responsibilities when blocks are read or written and when they learn of other caches issuing reads or writes for a block. True sharing and false sharing. True sharing cache misses occur whenever two processors access the same data byte. True sharing requires the processors involved to explicitly synchronize with each other to ensure program correctness. A computation is said to have temporal locality if it reuses much of the data it has been accessing. Programs with high temporal locality tend to have less true sharing. False sharing results when different processes use different data that happen to be co-located on the same cache line. A computation is said to have spatial locality if it uses multiple words in a cache line before the line is displaced from the cache. Enhancing spatial locality of minimizes false sharing. See data and computation as mentioned by Anderson, Amara Singh, and Lam. HTTP S2IF Stanford EDU papers, Anderson 95 paper.html. Multicore process advantages: cache coherency security operate at higher rate than off-chip, reduced power consumption for dual core or versus two coupled single core processor. Better quality communication signals, cache can be shared. Challenges, adjustment like this software, including OS, are required to maximize performance. Production yields down. An Intel quad core is in fact a double dual core. Two processing cores sharing the same bus and memory bandwidth may limit performance. High level of calls or core sharing and synchronization can easily overrun the advantage of parallelism. Concurrency platforms, pthreads, TBBB, Openmp, CALK++, race condition, CALK screen, MMM means CALK. Concurrency platform, programming directly on processor cores is painful and error prone. Concurrency platform, abstract code, handles synchronization communication protocols, optionally perform load balancing. Examples of concurrency platform, pthreads, threads, building block TBB, OpenMP, CALK++. We can use an implementation of Fibonacci sequence Fn plus 2 is equal to Fn plus 1 plus Fn to compare these four concurrency platform. Fib4, Fib3, Fib2, Fib1, Fib1, Fib0, Fib2, Fib1, Fib0. Key idea of parallelism, the calculations of the Fib n-1 and Fib n-1 can be executed simultaneously without mutual interference. Init Fib init n for n less than 2 return n, else init x is equal to Fib n-1, init y is equal to Fib n-2 return x plus y. Pthreads is a POSIX standard for threads communicating through shared memory. Pthreads defines a set of C programming language types, functions, and constants. It is implemented with a pthread.h header and a thread library. Programmers can use pthreads to create, manipulate, and manage threads. In particular, programmers can synchronize between threads using mutexes, condition variables, and semaphores. This is a do-it-yourself concurrency platform. Programmers have mapped that onto the computer resources, static scheduling. Key pthread function, init pthread underscore create, pthread underscore t, start the thread, return identifier for the new thread, constant pthread underscore attribute underscore t, star attribute, object to set thread attribute, null by default, void star function, void star, routine executor applies to creation, void star of a single argument pass to function, return error status. Init pthread join underscore pthread underscore t thread, identifier of the thread to wait for void star status terminating with threads status null to ignore, returns error status. Star Vim API threads provides similar functionality. Pthreads overhead, the cost of creating a thread is more than 10,000 cycles. This enforces coarse-grained concurrency thread pools can help. Scalability, Fibonacci core gets about 1.5 speed up for 2 cores for computing Fib40. Indeed, the thread creation overhead is so large that only one thread is used, see below. Consequently, one needs to rewrite the code for more than 2 cores. Simplicity, programmers must engage in error-prone protocols in order to schedule and load balance. Include stdio.h, stdlb, and lib.h, pthread.h, init n, if n less than 2, return n, else init x is equal to Fib n-1, init y is equal to Fib n-2, return x plus y, type to struct, init input, init output, thread underscore arguments, void star thread dot function, void star ptr, init I, thread underscore argument star ptr in the input, thread underscore argument star ptr output, Fib I, return null. Init main, init arguments charge and star rb, pthread underscore t pthread, thread args, init status, init result, init thread result. If argc less than 2, return 1. Init n is equal to ATY RPB 1. If n less than 30, result fib else arg start input is n minus 1 status p thread underscore create star p thread null thread function void star args main can continue executing result fib n minus 2 wait for thread to terminate p thread underscore join thread command null result plus args start output printf Fibonacci of percentage d is percent d backslash n result return 0. TBB1, TBB is C++ library that run on top of native threads. Programmers specify tasks rather than threads. Tasks are objects. Each task object as an input parameter and an output parameter. One needs to define at least the methods, one for creating a task and one for executing it. Tasks are launched by spam or a spam and wait for all statement. Tasks are automatically load balanced across the threads using the work stealing principle. TBB developed Intel and focus on performance. TBB provide many C++ templates to express common patterns simply, such as parallel or loop parallelism, parallel reviews for data aggregation, pipeline and filter for software pipelining. TBB provides concurrent container classes which allow multiple threads to safely access and update items in the container concurrently. TBB also provides a variety of mutual exclusion library functions, including locks. Class fib task, public constant long n, long star constant sum, fib task long n underscore, long star sum underscore n underscore sum underscore. Task star execute if n doesn't do star sum is equal to else y fib task and a is equal to star new allocate underscore child fib task n minus 1 star x fib task and b star new allocate child fib task n minus 2 star y set reference from 3 spam b spam and wait for all a star sum is equal to x plus y return none program match. OpenMP, several compilers available, both open source and Visual Studio runs on top of native threads. Linguistic extension to C, C++ are ported in the form of compiler pragmas, compiler characters, as pragma, OMP task shared X implies that the new statement is an independent task. Moreover, sharing of memory is managed explicitly. Other programs express a directive for scheduling, loop parallelism, and data aggregation, supports loop parallelism and more. Recently, in version 3.0, task parallelism with dynamic scheduling, OpenMP provides a variety of synchronization constructs, barriers, mutual exclusion, locks, etc. Init fib init n if n less than 2 to 10 n init xy pragma OMP stack task shared x is equal to fib n minus 1 pragma OMP stack shared y is equal to fib n minus 2 pragma p OMP task wait return x plus y. From CALK to CALK++, CALK has been developed since 1984 at the MIT Laboratory for Computer Science by Professor Charles Lesserson and his group, in particular by Matteo Vigo. Besides being used for research and teaching, CALK was the system used to code the three class chess programs, text, Socrates, and CALK chess. Over the years, the implementation of CALK ran on computers ranging from network of Linux laptops to an 1824 node Intel Paragon. From 2000, CALK has led to CALK++ developed by CALK outside and MIT spin-off, which was acquired by Intel in July 2009. Today, it can be freely downloaded. The place where to start is http://calk.com. CALK is still developed at MIT. http supertech csail.mit.us CALK. CALK++ respective CALK is a small set of linguistic extensions C++ respectively C. Supporting both joint parallelism. Both CALK and CALK++ feature a probably efficient for stealing scheduler. CALK++ provides a hyper object library for parallelizing code with global variables and performing reduction for data aggregation. CALK++ include the CALK screen, race detector, and the CALK view performance analyzer. Nested parallelism in CALK++ init fib init n. If n less than 2, 10 n init x comma y x CALK spam fib n minus 1 y is equal to fib n minus 2 CALK sync return x plus y. The named child function CALK spam fib n minus 1 may execute in parallel with its parent. CALK plus keyword silk spam and silk sync grant permission for parallel execution. They do not command parallel execution. Loop parallelism in CALK++, A and A transpose. Indices run from 0, not 1. CALK for init I is equal to 1, I less than n, I plus plus for init j is equal to 0, j plus n, I plus plus j. Double temp A of I comma j. A of I j is equal to A of ji, A of j is equal to temp. The iterations of a CALK for loop execute in parallel. Serial semantics 1/2. Silk, respective CALK, C++ is a multi-thread language for parallel programming that generalizes the semantics of C, respective C++ by introducing linguistic constructs for parallel control. CALK, respective CALK++ is a faithful extension of C, respective C++. The C respective C++ Ellison of a click. CALK respective CALK++ is a correct implementation of semantics of the program. Moreover, on one processor, a parallel CALK respective CALK program scales down to running the area as fast as C respective C++ Ellison. To obtain the serialization of the CALK++ program, define CALK for define CALK underscore spam, define CALK underscore sync. Serial semantics init fib int n. If n less than 2, return n, else init x comma y. X is equal to CALK spam fib n minus 1, y is equal to fib n minus 1 CALK sync, return x plus y. CALK++ source is init fib init n init if n less than 2, return n, else init x comma y fib x is equal to fib n minus 1 y is minus 1, return x plus y is a serialization program. Scheduling init fib init n if n less than 2, return n, else init xy self CALK spam and fib n minus 1 y is equal to fib n minus 1 CALK sync. Runs on the parallel. Scheduling CALK plus randomness work stealing scheduler. Load balances the computation at runtime. Each processor maintains a ready DQ. A ready DQ is a double-ended queue where each entry is a procedure instance that is ready to execute. Adding a procedure instance to the bottom of the DQ represents a procedure call being spawned. A procedure instance being deleted from the bottom of the DQ represents the process beginning in execution on that procedure. Deletion from the top of the DQ corresponds to the procedure instance being stolen. A mathematical proof guarantees near perfect linear speed up on application with efficient parallelism as long as the application has sufficient memory bandwidth. A swarm return in CALK is over 100 times faster than a pivot thread create exit and less than 3 times slower than an ordinary C function call on a modern Intel processor. We have the push, pop, and delete, QN and stacked. First, a spam happens in one of the processor. Then it happens in multiple processor. Then a return happens in next process. Return happens in the next process. Then empty, this one is there. Now stealing will happen. Once a stealing happens, it is formed. The CLK++ platform, okay. It consists of the program, a single threaded code, then CLK++ compiler, conventional compiler, linker, binary. Linker uses library, then runtime system, exceptional performance. Then from binary, it goes to CLK screen based detector, parallel regression test, enable multi-threaded code, and also to CLK view scalability analyzer. Trace bugs, one of the init x is equal to CLK for init I is equal to 0, I less than 2, I plus I, x plus asset x is equal to 2. Dependency graph, x is equal to 0, x plus asset x is equal to 2. Iteration of this CLK for should be independent between a CLK spam and the corresponding CLK sync, and the code of the spam child should be independent of the code of the parent, including code executed by additional spammed or called children. The arguments to be spammed function are available in the parent before the spam occurs. Now R1. Once it is R1 is there, then in one first x is equal to 0, R1 is equal to x, R1 is equal to plus, then R2 is equal to x, R2 plus, then x is equal to R2, x is equal to R1, then asset x equal to 2, R1 consists of 1, x is equal to 1, R2 is equal to 1. Watch out for races impact data structure such as struct character B, updating x.a, x.b in parallel can cause races. If an ostensibly deterministic CLK++ program run on a given input could possibly behave any differently than its serialization, CLK screen trace directly guarantees to report and localize the offending race, employs a regression test methodology where the programmer provides the test input and dynamic instrumentation of binary code, identifies file names, lines, and variables involved in the arrays, runs about 20 times slower than real time. Template type in empty, void, multiply, iter power, init II, init JJ, init KK, T star C, CLK for init I is equal to 0, I less than II, plus I for init K is equal to 0, K less than KK, plus K, CLK for init J is equal to 0, J less than JJ, J plus J, CA of I star J, J plus J, plus equal to A, I star KK plus K, plus B, K star JJ plus J. Does not scale up well due to poor locality and uncontrolled granularity. Template type empty, void, multiply, record, sequential by init I is equal to 0, init I is equal to 1, init J0, J1, K0, K1, T star A, PTR diff underscore T LDA, T star B, PTR diff underscore T LDB, T star C, PTR diff underscore T LDC, init DA is equal to I minus 1, I1 minus I0, DJ is equal to J1 minus J0, DK is equal to K minus K0, if DA greater than or equal to DJ and DA greater than or equal to DK and DA greater than or equal to recursion threshold, init MI is equal to I0 plus DA by 2, multiply record sequence helper I0, MI J0, J1, K0, K1, A, LDA, B, LDB, C, LDC, multiply record sequence helper MI I1, J0, J1, K0, K1, A, LDA, B, LDB, C, LDC, else if DJ greater than or equal to 0, equal to dk and dj greater than equal to recursion threshold. Init mj is equal to j0 plus dj by 2. Multiply record sequence helper I0, I1, IJ, mj, k0, a, LDA, B, LDB, C, LDC. Multiply record sequence helper I0, I1, mj, j1, a0, k1, A, LDA, B, LDB, C, LDC. LCF dk greater than equal to recursion threshold if mk is equal to k0 plus dk by 2. Multiply record sequence helper I0, I1 is around k0 mk A, LDA, B, LDB, C, LDC. Multiply record sequence helper I0, I1 j0 mk is k1 A, LDA, B, LDB, C, LDC. Else for unit I is equal to 0, I0, I less than I1 plus I. For unit K is equal to K0, K less than K1 plus K. For unit J is equal to J0, J less than J1 plus J. C I star LDC plus J plus equal to A I star LDA plus K star B K star LDB plus J. Template T, type name T, inline void multiply record sequence init II, init JJ, I T star B, T star C, multiply record sequence helper 0 II, 0 JJ, 0 KK A, KK B, JJ C, gamma J, multiply 4000 by 8000 matrix by 8000 by 4000 matrix on 32 crore 8 sockets and 4 cores, quad core AMD Optron 8354 per second. The 30 core share L3 32-way set of cache up to megabytes. Core license parallels speed up 8 420.906 1.365 8.1 speed up 16 core it is 432.419 and 25.845 16.73 speed up 24 it is 413.681 17.361 23.83 speed up 32 it is 389.300 seconds parallel it is 13.051 seconds and 29.83 speed up.